Hello, so this is the last part of my summary of lecture 20, the inverse Cramer's rule and the volume. So let's discuss about how the determinants connect to the volume. And the main point here is that actually with determinant we can compute the volume or the area in case of 2 by 2 without having to, avoid some complicated computation of the length, height, and something else. We'll go back into this point. But the first part is that showing how our definition of the area also satisfy the first three properties of the determinant. So the first one, let me write that down, the identity is equal to 1, the determinant. And the determinant of reverse row order will also reverse the sign. And the third one is the multiplication and the additional rule of a single row. So let's see that one by one. So what about the identity matrix? Let's see a really simple example and draw them on a plane. So we have obviously a square with an area of 1. So the first one checks. And the second one, what happens if we exchange row right now? So it might be look like this. Oh, it not might be, it is look like this. And then what do you imagine if that if this goes also to n by n, or even in this case it just switch up the drawings into the opposite dimension, right? So it might look like this, which you have the -1, 1, and then you have the area of -1. And even if you don't have the area of a unit area, let's say you have some area with 8, and then you will end up with -8. But the sign will change, but then the magnitude doesn't. So in the end, if we talk about the volume, we only interested in the magnitude itself, whether it is still 8 or does it change. Is that consistent with 8? We don't care about the sign. So for the second part, this also checks because the magnitude is still the same, only refers to sign. That's okay. And the third part, so let's take it one by one. So multiplication. So what happens if I multiply this one by let's say 5 0 0 1? So can I do this, and then my area will be 5? Of course, yes. So if I just extend the x-axis here to 5, and then I still have 1 of height, so this area will be 5, right? So this one checks out. And then the second part is what if I add something to my first row? So let's say you add the first row by 3. So I might not have the best picture right here. So let's see what I can do. 4 3. Header again, sorry I stopped there a while. So I was thinking how to best visualize it, but maybe this is the best thing. So you have like this is 0 1, and then 0 1 here, and then you have this 3 3 here, and then this will be add up to the 4 3, and then you end up with this area right here. So this is like the original A. This is, I can say, A accent. So this will be equal. Remember, if we do that term, so this will be like this. So in the end, you're just kind of attaching that A accent to the A. There's a better picture in the book that describe all this, so you might want to check them out. I suggest you to check them out. So let's move on to some example that kind of brings me back to the point that I made earlier. So let's delete all of this. So let's say I have 2 points of A, B, and C, D. And then let's say I end up with some kind of parallelogram. Sorry, I'm having a hard time pronouncing it. AB, and then there is this one is our C and D, and this here is A plus C, B plus D. So we are interested in the area of them, of this parallelogram. So if we just use our usual formula from to compute a parallelogram, we might need to first compute the base of it, the length of this one, and also times the height of it, which is I think this one. So as you can see, there's a lot of like root involved. You need to compute first this length and this length squared, and then you need to compute the Pythagoras of them. You need to have this term also compute that, the height, and it gets complicated, right? So this is really complicated computation. But the idea of determinant also gives you the volume and the area in this case in terms of 2 dimension. You just need to compute the determinant of if you place that on the row. So the determinant of this matrix will gives you the area. So isn't that really easy to compute compared to the first one? So that's, I think, the main idea that this section about determinant being volume wants to give us, that you can compute the determinant really easily without having to know the length or the height or anything that you need to compute the area. And another thing that the book mentions about also the area of triangle in this case. So if you were asked to compute the area of triangle that has this point of AB and CD, which is this triangle right here, so you can do compute first the determinant of them and then just times half the determinant of them. Okay, but this only works if you start from the origin. So what happens if you are asked some triangle that is not start at the origin, so you were only given a set of 2 points, 3 different set of 2 points, 2 coordinates, the xy coordinates. So there's a really neat formula in the book, so I'll just give them here as well. So let's say you were given x1, y1, x2, y2, x3, y3. So you will end up with some triangle somewhere in the plane, and you can compute the determinant, the half of the determinant of this matrix. And that's it. So this is the area of the triangle. And that's it for my summary of lecture 20. Thank you.